we discussed distributions, right? Looking at a histogram, is it skewed to one side? So throwback to, oh my god, come on. These, right? Skews. If they're skewed to one side or not. And the one in the middle is symmetric. So if it's symmetric, we say it's a normal distribution. Right? Normal distributions are symmetric. The mean, median, and mode are all around the center. So skews are when you have distributions that are off to one side, but the whole point of 11.3 is the normal distribution. So this is the most important one. If you take stats next year, this is you're gonna learn more about this, whether it's AP stats or regular stats.
Like the normal distribution.
Yeah, you're gonna really go into it. This is a little taste of what next year would be like. Also, I was told AP stats is a lot of writing. So
What do you mean writing?
literally like words and paragraphs of words. Yeah, lots of writing. It's not as much computing. A lot of critical thinking, not as much like regurgitation, but more like analysis.
Oh, good. That's good.
Yeah. So if you can do calc and AP stats, or you can just do stats or just calc, whatever. You do you. I won't take it personal, whatever. Because honestly, if people take calc, they need to be with it their senior year. That way they don't end up in March being shenaniganville. Because that's rough. Okay. So, normal distribution, it's a continuous probability distribution. Okay, what does this mean? It doesn't touch the x-axis. It's this nice bell curve shape, and it goes on forever in both directions. It's symmetric with the mean, right? So it's not skewed at all. The mean, median, and mode are all the same number and are located at the center, right? So here, this number is where my mean, median, and mode are. The curve is continuous. There's no breaks in it. So notice the more values I have, right? N is the number of data points. The more values I have, the more smooth it is. So eventually you have your whole population, which is a very large number, and it's going to be a nice bell curve shape. The total area under the curve is 100%. Cool. So far so good. So recall standard deviation is the measure of how far values differ from the median, from the mean. So the bigger your standard deviation, the more variance you have, right? The more spread out your values are. The smaller your standard deviation, that means your data points are closer to the mean. They're more grouped together. So standard deviation measures how different each data value is from each other. If the standard deviation is small, that means all your values are close together. If your values are spread out all over the place, you're going to have a very large standard deviation. It has the same units of measure as the original data. And for many data sets, a value is unusual, right? It's a weird value if it's different from the mean by more than 2 standard deviations. So the example I gave in the other class, so this is where I'm at right here. The example I gave in the other class is when I was doing my undergraduate thesis, literally I had to take into account every single thing that could cause my star to dim besides the star itself, right? Did a cloud pass in front between my telescope and the star? Was it my sensor? Maybe there's some faulty pixels. Maybe it's the fact that my star is getting closer to the horizon, so it has more atmosphere to go through, right? More air blocking it. There could be a smudge on my lens. Like, why is this pixel changing, right? Why is this one so much different than the other? So having to be very... I'm trying to make this as simple as possible, but I dealt with standard deviations and probability distributions and all of these things just to prove that yes, this star is changing because it literally is brightening and dimming. It's not because any of the other factors. So you have to look for unusual data. There'll be more examples next year if you take stats. And it's also very useful when you have different sets of data to compare their standard deviations to each other, because I do this all the time, especially between my 2 sections of the same class. Okay, why is my F period spread out everywhere where G is very much localized or something, right? It just one way. All right. So if you took the PSAT in October, there is a question just like the second graph. And it was dealing with a changing mean, what happened with the, if your median changes, what happens to the mean, etc. This is one reason why we're going over this. Helps you critically think, but also it's tested on PSAT, ACT. So the shape and position of the normal distribution depends on two things, right? The shape. Your mean is your average. So wherever you're centered around is your mean. And then your standard deviation depends on how like skinny your bell curve is. If you have a very small standard deviation, it's going to be a nice like mountain, versus a wide distribution, it's going to be more spread out. So for a larger standard deviation, the curve is wider, right? The curve will be wider. So notice it's like blue versus red. Hopefully you can tell the difference. It's not so easy when it's on your paper. But here you notice that we have the same mean. And we know this because the peaks are at the same point horizontally. So notice that we're using sigma and mu because this is for the overall population, right? So before, when we used standard deviation, we said, oh, SX, because that was for a sample. Now we're talking about these are for populations. Before, when we talked about mean, we used X bar because that was for a sample, right? Mu is the mean for a population, just to make sure we're like all groovy with what we're talking about right here. So bigger standard deviation, more spread out, it's a wider curve. Now, if the mean of the data set changes, this means the graph is going to shift horizontally. All right, so what I want you to notice is literally right here, the mean increased. All right, if our standard deviations of the two data sets were equal, means the mean increased for it to shift up. So I probably debated for like an hour back and forth if I wanted to go over this lesson with you guys, but I think it's useful. Mainly because you hear stats all the time in like the news. It's helpful to like have the ability to understand them and critically think about them, especially right now, for instance. And this is not even political. There's so much misinformation about the coronavirus and like percentages and blah, blah, blah. And like, oh my God, it is, 3,000 people died or something. Well, you look at the percents. The people who are really, really in trouble are the ones who have chronic illnesses. They're old. Old men with diabetes. Ugh. Yikes. You look at the people who die in the United States, like that's who it is. So if you're young, healthy, we are part of that for the most part. Wash your hands. Don't touch your face. Probably be okay. Don't go near sick people, but you'll probably be okay, right? There's a lot of misinformation. People are throwing out random stats. I don't know. Maybe it's just because I have a lot of connections with ignorant people in Nebraska that they just don't understand. Okay. I don't know how to say it nicely. So empirical, the 68, 95, 99.7% rule. So what this means is if within one standard deviation of your mean, 68% of your data is within one standard deviation. Guess what? 95% of your data is within 2 standard deviations of your mean. That's rad, right? That's pretty cool. This is what you did in psych. And then if you're within 3 standard deviations, that's 99.7% of your items. 99.7% of your data will be within 3 standard deviations of your mean if you have a normal distribution. Cool. So 68% within 1 standard deviation, so that's 1 standard less, 1 standard deviation above, and that's 68%. So if you divide that in half, that means you have, the 34% above, 34% of your data lies between the mean and 1 standard deviation above. 34% lies within the mean and 1 standard deviation below. Coolio? Okay, I'm trying to do a better job explaining it than I did the last class, because otherwise it will make the problems easier near the end.
Are we doing Z-score?
Yes. Did you do it in psych? Because you learned the vocab word but didn't calculate it, right?
Yeah. I did it last.
Ah. Yes, you did. You did. This is all from, this is all from Trig.
Mm-hmm.
So, because we share the same book, and so we have the same like stat unit. Cool. Well, as long as you know it, that's rad. You can help. Man, your partner is just gonna love you because you're like good on it. Who should I stick you with? Just kidding. I'm gonna do a random generator online. It's not even gonna be me selecting. So, I'll like click it like 3 times. I'll make sure no one's with their besties. So, yeah. Yep. Okay. 95% of the values fall within, I don't know. I told you, random generator, I gotta believe it. Within 2 standard deviations. So, to go from 68 to 95%, that's an additional 27%. So, that means, half of 27 is an extra 13.5% on the left, 13.5% on the right. Because if you total this whole area, add all these together, you're going to get 95% of your data. Within 2 standard deviations less and 2 standard deviations more, that's 95% of your area, 95% of your values. And then if you have 3 standard deviations, okay, ready?
4.
It's just not useful. 99.7% of your data is the majority of it. Because if you have data points that are outside that, most times you're going to look at them individually because it's 0.3%. So it's very, very few. And you're like, okay, you're going to look at all your outliers and decide, can I keep it in my set? Can I exit it? So I'm trying to think of a solid example right now of times when I've actually kept my outliers.
Like in test scores.
Oh, here's an example. One of my classes, the average was a 70% on a quiz. Just kidding, it was a 72 because an outlier, someone got 104% on my quiz. No curve, I couldn't curve. The next highest score was a 76. Yeah, so that's definitely an outlier. It was more than 3 sigma away. And that's because they studied. They came to bonus, they studied, they slept the night before, and they took it serious. Okay, so 3 standard deviations, so we have the 68%, and then, add on the 13.5 on both sides, that's 95%. So we have an additional 4.7%. So if you divide that in half, that's going to be 2.35 on each side. An additional 2.35%, which means this is 0.15% extra, 0.15% extra. This is being exact because this is exactly what the book does. I don't know. This simplifies it a little too much. So if I say, okay, let's just do the examples. Does that make sense how we're breaking the percents up? Because if 95%, okay, cool. So half of that 95% versus the other half 95%. I'm very much a visual person, and so these graphs, that's how I learned it. Okay. IQ scores have a bell-shaped distribution with a mean of 100 and a standard deviation of 15. What percent of IQ scores are between 70 and 130? Just draw a picture and then we can discuss it. So, I'm going to draw myself a little bell curve. Okay, so I know that here, it's close enough, okay? Not perfect, close enough. This is 100. So that means 1 standard deviation below is at 85. 1 standard deviation above is at 115. Okay, let's go another time. So now the second standard deviation below is 70, right? Because that's 1 sigma, 2 sigma, right? 2 standard deviation. 1 sigma above, 2 sigma above. I am not an artist. Please forgive me. Okay. But hopefully this makes sense. It's kind of like what we were doing up above. So we want to know what percent of IQ scores are between 70 and 130. So 70 is 2 sigma below, 130 is 2 sigma above. So if we are all the values within 2 sigma, what percent is that going to be? 95%. 2 standard deviation, this is going to be 95% of your values.
What's IQ score on a scale of?
Does it go up to like 200 and something? Because it depends on your age. The older you are, the harder it is to get a higher score or something. You're considered like genius if you're above like 130. I think it's like 140 something. So that's interesting. So 95% of your values are within the shaded region, which means 2.5% are here and 2.5% are here. So technically, if you score above a 130 on an IQ test, you're the top 2.5% of the world. You know, so that's something to do with like Mensa. You can be smart enough to join them. Yeah.
Does it mean with what?
You know, like Mensa makes you do these tests. You have to have a certain IQ to get into Mensa. Mensa is this like society for pretentious jerks who think they're like smarter than everyone. I'm sorry if you're part of Mensa or your like parents are or whatever. I just refuse to join it. Like, why? Like, they wear like I'm so smart at Mensa. Okay, people should know you're smart without you telling them. Okay, that's just me. It's 2:50 today. That's what time it is for me. Okay, it is 5th class o'clock. Okay. You guys always catch me with my 5th class days. Okay, ready? Example 2. Let's go. Oh, sorry, are we good with the 95% within 2 standard deviations? Okay. The heights of 880 students at East High School are normally distributed with a mean of 67 inches and standard deviation 2.5. Cool. How many students are more than 72 inches tall? Okay, so I'm going to draw myself a little bell curve it out. All right, I'm going to label my heights and such. So the average was mean. Okay, 67. So this is 67, right? Ugh, I'm not drawing good today. Okay, 1 standard deviation. Okay, so 1 standard deviation less is, let's see, 64.5. 1 standard deviation more, 69.5. 2 standard deviations more, so add another. Okay, so that's 72. Is mine okay? Can you see like the dot versus the line versus solid? I'm trying to like show you the difference. Okay, subtract another 2.5, so 62. 62, yeah. Okay, so we want to know how many students are more than 72 inches tall. Okay, so what we're looking for, this is my mean, so I'm looking at this area. This whole area I just shaded in is literally 50%. Cool, because that's just half my graph. Now the dealio is, I only want to know about this section right here. How many are more than 72? Well, we know the percent breakdown, right? This is 34%. This is 13.5%. So if you add those up, that's going to be 47.5.
Exactly how many are more than?
More than 72. So the people, so all the ones between 67 and 72 are 47.5. So that means all the ones above 72 are going to be 2.5%.
Yeah.
So this part right here is going to be 50 minus 47.5, which is 2.5%. Okay, because what I did was I said, okay, here is the median. I know half are above. And then I know the breakdown, right? Within 1 sigma is 34. Within the, second sigma, between the first and second sigma is 13.5. So it means the whole thing 50 minus this 47.5 is what I have left, which is the 2.5. We want to know how many students are this tall. Well, 2.5% of our population. So you do 2.5% of 880. So you just multiply 0.025 times 880, and you will find 22 students. I thought it was like a 5-minute thing, my bad. Click on, okay. Whatever. Screencast it up. Woo! Ooh, if you listen to the screencast, come in tomorrow and say pancakes. Hey. I won't say bacon because that's not kosher. If you listen to the screencast, come in and say bacon. That way I know you listen to it. Yeah. So I'm gonna start doing. Okay, questions? So the key here, how many are more than 72? So we're only looking at the region right as 72 because that's just more than. Okay, what percent are between 59.5 and 69.5 inches tall? So I'm going to come back up to my original graph. You know what? I'm going to actually go to cheat for 2 seconds. Okay, let me copy this, duplicate. Ugh. Okay. Perfect. Okay, let me erase some of this. So this problem, we're trying to find between, ooh, I don't have it on there, 59.5 and 69.5. Okay, so I need to add one more sigma on my left side. So 62 minus 2.5. This is going to be, I don't know how to, maybe I'll make it like ziggy zag. There we go. 59.5. So we're trying to figure out this area right here, 59.5 to 69.5, this area. Okay, so we know that this is 34%, this is 34%, we know this is 13.5, and then we know that this is 2.35. Right, because we went over the percentages before, speak now or hold your peace. Are we cool? Are we okay with these percents? Because we went through how we divvied it up at first. So you just add them all up. 2.35 plus 13.5 plus 34 plus 34. It's going to be 83.85. No, yeah. 83.85%. Okay, so wow, that's a lot of kids between those two heights. All right, recall in the last section, all right, what we just finished yesterday, it was useful to have two box plots on the same graph. We can compare the data sets by looking at these two box plots. In particular, we looked at the home run scores, home runs by baseball players in 1927 and 2007. So it's also cool to compare the location of certain data values within the same data set. Or like how far are we? So you can talk about how many sigmas away you are from the mean, right? How extreme are certain values from each other? So the z-score is literally the number of standard deviations a data value is above or below the mean. Like how many standard deviations are you away from the mean? Yeah, sorry. So I'm going to get, I'll give you the equation, whatever, I'll write it on the board.
How did you get 13.5?
Okay, so up here, 13.5.
Oh.
Yeah. Because, yeah, so I broke it up here. Since we had 27, going from 68 to 95 is 27. Divided by 2, that means we're going to add 13.5 on both these sides. Percent-wise, so that way total it adds up to 95. Okay, so z-score, I'll just write this on the board, whatever, I'm trying to trick you. Keep in mind, right, the mean, x-bar, or mu, depends if we're looking at a sample, or if we're looking at the whole overall population, mean, whatever. And z-score is always 2 decimal places. X is data value. X bar, mean. Sigma, standard deviation. That's it. It's not too bad. And it's just going to tell you how far away is this certain data value from your mean. Right? The further away it is, the higher the standard deviation. And if it's a big enough number, it's going to be special. Like, you always want to really look at the really outside outliers. Like, why? Why is this so high? Why is this so low? Was this a fluke? Was this a mistake? Is this, is it significant? Okay. The next 3 problems we're doing are similar to ones on the quiz. So there 3 of your 16 problems. Okay, so keep in mind z is equal to, right, the z-score, how many standard deviations a data point is away from the mean. All that is your data x minus x bar, your mean, over sigma. So here, 24 minus 29 over 4.2. And order matters. You have to follow the order of operations. So you see z is equal to negative 1.19. What this means is our data value, 24, is 1.19 sigma below the mean. So this could stand for ACT scores. Probably not, right? The average ACT score is definitely not a 29, but let's just say it is. So if the average is a 29, our data value is 24, and our standard deviation is 4.2, 24 is 1 and about a fifth sigma less than the average. It's smaller than the average. Yeah. Okay, we can try the next one. So we're trying to solve for x, so keep in mind, I'll write this equation on the board for you. Don't forget, it's a little partner quiz, 16 problems. Okay, so personally, and when I taught physics, I like to solve for my variable first before I plug in. So multiply both sides by sigma, add my mean. It's going to be x. So I have negative 1.73 times sigma 2.3 plus my mean, which is 48. So you get like 44.021, except what we're going to do is we're going to round to the same place as the mean. So I'm going to say x is equal to 44, and I'm going to round to the same place as the mean. Okay, so two problems just like this. I don't know, I don't think it's too bad. It's just you have to know where to plug it into. And if I give you the equation, it's a little less for you to remember. It should be easier. Okay, example 4. Consider a comparison of two individual data values as we try to determine which is more extreme, right? So both of these things are outliers, but like which one is a bigger like cause for concern? Like which one is really concerning? Which one's way more extreme? All right, the 76.2 inch height of a man or the 237.1 weight of a man. Okay, we can't compare them directly. The weight versus inches, I don't know. Which one's more like out of the norm? So what we can do is compare the data values by looking at their z-scores. How far are they away from the mean, right? Their standard deviations away from the mean. So we're going to do two different ways. All right, so first I'm going to look at the z-score for the height. So I take the data value, right? He was 76.2 inches tall. I subtract the mean, right? The mean of the height was 68.34. And then I'm going to divide by the standard deviation. Standard deviation is 3.02. So the z-score of my height is just 2.60. Remember, it's 2 decimal places. Now, let's compare this to the z-score of the weight. So remember, the data value, his weight, is going to be 237.1. Let's subtract the mean, which is 172.55. And I'm going to divide this all by the standard deviation, which is 26.33. So the z-score of the weight is 2.45. So we can answer our question now, right? The height is more of an outlier than the weight. This is a way to compare different data values. Which one is more extreme? Height. All right, and then the last, so like this is the important part. I'm going to show you how to do it on your calculator. Come on, okay. So if you push the library key, and you push like you can scroll down to where it says in.
Wait, where's the library?
It's the little book underneath the delete key on the right side. You can just scroll down till you see INV norm. It's like inverse norm, whatever. You just push enter. Okay, so that's how you find it. And then once you do it once, you can always like, I'll click back up and show you. I think I should have did that after I actually set up the problem. Okay, so we want the middle 50% of our data. So what we did was we said, okay, here is We found z-scores, but what if I want the z-scores for a given area, not the opposite way around? So the middle 50% of the data, let me draw this first and then I'll show you, like, again, how to do it. I kind of went out of order in my head a little bit.
Wait, how did you find the INV norm?
I just scroll down.
Oh.
Yeah. So the middle 50% of the data is here, right? So that means I'm going from the 25th percentile to the 75th percentile, right? 25% on each side. Is this going to be more than, less than 1 standard deviation? Remember, standard deviation would be like 34% on both sides, where here we only have 25. So we're going from 0.25 to 0.75 because we want the middle 50% of the data. So the middle 50% is from the 25th percentile to the 75th percentile, the middle 50. Okay, so let me come back over here and show you how to do this. Okay. So I click on the library key. If I say I just like scroll down. I'm trying to think if there's a quicker way to do it.
You can just click I, and then
And scroll down to I, and then you scroll down.
You just scroll down to find it.
Yeah, so that's what I'm telling people. I'm trying to think if there's a faster way of like finding this though. No, okay, I didn't think so. So if you put in 0.25, because that's my left bound, and push enter, you see one of the z-score. You see the z-score. Then, ready? Here's a faster way. If I click the up arrow key, oh my god, where's my arrow? Click the up arrow till it highlights this, push enter, guess what? It pops up. I can just scroll over and change the number. Like, once you do it once, it goes a little faster.
Wait, but how does it know the z-score if it doesn't know the standard deviation?
Because it's the normal. We're using the normal distribution. So with a normal distribution, the standard deviation is 1. Yeah, and the mean is around 0. So it's like a very special case, yeah. Because this is all for normal distribution. Okay, so that means the z, all the normal distributions all have the same exact like form.
But even if the standard deviations are like closer together or further apart.
So the middle 50% of the data is always between these two z-scores.
Right. Okay.
It doesn't matter the like standard deviation. Yeah. So we want z-scores that are greater than the one for the 0.25 and less than the one for the 0.75. AKA, my z-scores are between 0.67 and positive 0.67. Because I'm between, right? The middle 50, I'm between those two. Yep. So this is just a calculator question. I think there is 1 or 2 like this. I forget, I gotta look. Okay, so now we want the outside 20% of the data. So here's the 10th percentile. Here's the 90th percentile. So I want the outside, the first 10% and the last 10%. So we enter it as 0.1 and 0.9. So once again, I just go over to my calculator and I just like scroll up, push enter, bring it in, and put the percentile. Scroll up, enter. Like once you find it once in your library, you can just quickly go through the rest of them. Okay, so you can see the numbers. Cool, okay. Okay, so notice we want the z-scores to be less than the one for the 0.1. So it's going to be the z-score has to be less than negative 1.28, or the z-score has to be greater than or equal to the 1.28, because we want the outside, right? So it's kind of like you have, I don't know, all these inequalities. We want the outside, so it's an or. Notice that part A was an and because we wanted the inclusive, the inside. Yeah, and then that's it. So I'll stop the screencast.